All right, today we're going to do something fun. We're going to take this beast of a 4x4 matrix and find its determinant using a classic method, one that's been around for centuries. Now, it might look intimidating, but trust me, there's a secret weapon hidden inside that's going to make this whole thing way easier. Okay, let's jump right in. So here it is, our 4x4 matrix. The big question is, what single number can unlock the secrets hidden inside these 16 values? That number is the determinant. Our mission, should we choose to accept it, is to figure out how we get from this big grid of numbers down to just one.
To get there, we're going to dust off a formula from the 17th century, cooked up by the one and only Gottfried Leibniz. And I'll give you a heads up, it can look like a bit of a monster at first, but it's absolutely the key to solving our puzzle.
And here is that formula. Now, don't let the Greek letters scare you. The idea is actually kind of cool. We're going to create a bunch of products. And to do that, we have to pick one number from each row and each column. The catch is, no two numbers can share the same row or column. It's kind of like a game of Sudoku, right? Once we have all those products, we just have to add or subtract them based on a special rule.
So for our 4x4 matrix, the formula tells us we have to calculate 4 factorial. That's 4 times 3 times 2 times 1, which is 24 different products. Phew, that's a lot of number crunching. But what if I told you there's a hidden shortcut, a way to cut that number in half before we even start?
And that shortcut? Well, it's been hiding in plain sight this whole time. A closer look at our matrix reveals something really special, a feature that's going to save us a ton of work.
Take a look at the second row. See those two zeros? They are our secret weapon. Now remember, every single term we're supposed to calculate is a product of numbers multiplied together. And what happens when you multiply times anything by 0? Well, the whole thing just becomes 0.
So this means any of our 24 potential products that happens to include one of those zeros just vanishes. It turns into 0. We can just toss them out. And just like that, half of our work is gone before we even started.
And poof, we've gone from 24 terms all the way down to just 12. Much more manageable, right? So now the only question is, which 12 products are left?
All right, time to play detective. Let's figure out which 12 products actually survived that cut and are still in the running.
You know, for a product not to be 0, we have to pick a number that isn't 0 from that second row. Looking at our matrix, our only options are the 6 in column 2 or the -9 in column 3. So that actually splits our problem into two smaller, more manageable groups to investigate.
Okay, so we know which products to calculate, but now we have to figure out that last part of the puzzle. Do we add them or do we subtract them? And to do that, we need to talk about something called inversions.
An inversion sounds complicated, but it's really not. It's just a pair of numbers in our list of column choices that are out of order. So, if we picked columns 1, 2, 3, 4, everything is in its natural order. That's perfect. But if we have something like 4, 3, 1, 2, things are a bit jumbled. We just count up how many pairs are out of whack. If that count is an even number, we add our product. If it's an odd number, we subtract it. Simple as that.
Let's walk through this example together. Let's say we have the permutation 4, 3, 1, 2. Okay, first, we look at the 4. Is it bigger than the numbers after it? Yep, it's bigger than 3, 1, and 2. So that's 3 inversions right there. Now for the 3. Is it bigger than what's left? Yep, 3 is bigger than 1 and 2. That's 2 more inversions. So in total, we have 5 inversions. And since 5 is an odd number, the sign for this term is negative. We're going to subtract this one.
Okay, let's put it all together. Here are the first 6 products we need to calculate. These are all the terms where we chose the 6 from that second row. Check out the first one. The permutation is 1, 2, 3, 4. Perfectly in order, so 0 inversions. 0 is an even number, so the sign is positive, and our term is -3240. Now look at the next one. 1, 2, 4, 3. Here, the 4 comes before the 3, so that's 1 inversion. 1 is odd, so the sign is negative. But wait, the product itself is -180. A negative times a negative gives us a positive 180 to add to our total. See how that works?
And here are the other 6 products. These are the ones where we picked the 9 from the second row. Let's look at the first one here. 1, 3, 2, 4. The only pair that's out of order is the 3 and the 2, so that's 1 inversion. 1 is odd, so our sign is negative. The product is -5400, so a negative times a negative gives us a positive 5400. Let's jump to the last one, 4, 3, 2, 1. This thing is completely backwards. We've got 6 different pairs out of order. Since 6 is an even number, the sign is positive, and we just add the product of 900. So, we did it. The heavy lifting is over. We found all 12 of our non-zero products, and we figured out whether to add or subtract each one. Now,
for the moment of truth. Let's add them all up. Here they are, all 12 of our final values, ready to go. All we have to do now is add and subtract our way down the list to finally reveal that single number that defines our matrix.
And there it is, 5,835. We started with 16 numbers and what looked like a really crazy formula, but by working through it step by step and using a clever trick, we've boiled it all down to just one number.
You know, the permutation method might not be the absolute fastest way to find a determinant every time, but it does something beautiful. It shows how a single, really meaningful value can pop out of a complex system of rules. It really makes you wonder, doesn't it? What other complex things in our world are built on foundations that are just, well, elegant?